Hello, and welcome to another Reigate Maths video focusing on the second year of the Decision 1 topic for the Further Maths syllabus. My name's Simon, and this is the first of a number of videos focusing on the Travelling Salesman Problem. This is a huge topic in the second year, and it is really something that you need to know how to do. The main thing with the Travelling Salesman Problem is there are actually two versions. There's the classical Travelling Salesman Problem, and the practical travelling salesman problem. Overall, the principle of the travelling salesman problem is that you have a bunch of cities that are connected by roads, and you're trying to get to every single one and return back to where you started. So a travelling salesman might start at their home and travel to every town exactly once to sell their wares. Now, in the classical problem, the aim is to visit each town, so each vertex, exactly once before returning home. Now, for some networks or some graphs, that might be possible, but it's rarely the case. So often, we have to look at the practical travelling salesman problem, which is we visit each vertex at least once before we return home. Typically, how these problems work is that the actual reality is that we are looking at a practical travelling salesman problem. But in order to do the maths and the algorithms, we need to turn it into a classical travelling salesman problem. By finding matrices of least distances, we can do that, because the classical travelling salesman problem relies on the graph being complete, which, as you can see, this graph definitely not. The whole point of the travelling salesman problem, classical or practical, is trying to find the best, shortest, cheapest, optimal way of visiting either each vertex at least once or each vertex exactly once in any given network. The problem with that is it's very hard to do. This is a problem that has puzzled mathematicians for a very long time. There's lots of very important terminology in terms of high-level mathematics, looking at things like NP completeness, that, to be honest, I don't really understand. But this problem means that it is very hard every single time for every single problem posed to find the exact solution. So instead, what we do is we use what are known as heuristic algorithms. These don't necessarily find the optimal solutions, but they generally find ones that are good enough. Sometimes the algorithms we'll use do find the optimal solution. Sometimes they work, but they don't work every time. Heuristic just means they're good enough. What we are going to be looking to do is find an upper bound and a lower bound to give us a region for what our answer could be. To continue with this introduction, we're going to look at a little set of terminology. The first term is called a walk. Now, a walk is a finite sequence of edges such that the end vertex of one edge is the start of the next. So what that means is, if we've got our first arc or edge in a sequence, if we jump from A to B and then we also want to go from C to D, in order for it to be a walk, we have to join it up. Okay, we can't go A to B, then jump to C, and go to D. We're not allowed to do that. That's not a walk. A to B to C to D is a walk. A tour, and then we go back to the start. Often. A tour, which is the most important term in this set, is a walk which visits every vertex and returns to the start. So this is a tour. The key thing with what we're doing is finding these. That's what the travelling salesman problem is all about, is finding tours and picking the best one. Now, as I said, that's not always possible. So what we do instead is we find an upper bound, which is the highest value our optimal tour could be. We find a lower bound, which is the lowest value our optimal tour could be, and our answer is going to be somewhere in between the two. We might find several upper bounds, and we might find several lower bounds. So we need to look at selecting the best upper bound or the best lower bound, and that's something we're going to do in future videos. But these are really important terms as well, but tour is the word that is going to come up most, because that is what we're trying to find. Typically, in order to start a travelling salesman problem, you need to find what's called a table of least distances. This basically turns any network into a complete graph so that we can use any of the algorithms that we can use for a classical problem and apply them to a practical travelling salesman problem, which is much more realistic. Now, you might have to do this in a couple of different ways. An examiner could, for instance, ask you to do Floyd's algorithm first as kind of a part A of a question to generate this table of least distances. They might, like we're going to do with this one here, just get you to do it by eye. Sometimes they won't get you to do it at all, and they'll give you a table of least distances. And going forward in future videos, that's what we're going to do, is I'm going to give you a table of least distances, but it'll be the same one for the next three videos, so that we can build up a problem or build up our solution to a problem using the same network. Okay, but first, just very quickly, what I'd like you to do is pause the video and use this table given here to find a table of least distances. And this is what you should get. Now, hopefully that wasn't too tricky. As I said, you might have to do an algorithm first to find that. You might have to do it yourself, like we've just done here, or you might just be given it. Either way, once you have this table of least distances, you can then go forward and apply the next set of algorithms to find some form of solution to the travelling salesman problem. Thank you for listening.